Electronic engineering, also called electronics and communications engineering, is an electrical engineering discipline which utilizes nonlinear and active electrical components such as semiconductor devices, especially transistors, diodes and integrated circuits, to design electronic circuits, devices, VLSI devices and their systems. The discipline typically also designs passive electrical components, usually based on printed circuit boards. Electronics is a subfield within the wider electrical engineering academic subject but denotes a broad engineering field that covers subfields such as analog electronics, digital electronics, consumer electronics, embedded systems and power electronics. Electronics engineering deals with implementation of applications, principles and algorithms developed within many related fields, for example solid-state physics, radio engineering, telecommunications, control systems, signal processing, systems engineering, computer engineering, instrumentation engineering, electric power control, robotics, and many others. The Institute of Electrical and Electronics Engineers (IEEE) is one of the most important and influential organizations for electronics engineers based in the U.S. On an international level, the International Electrotechnical Commission (IEC) prepares standards for electronic engineering, developed through consensus and thanks to the work of 20,000 experts from 172 countries worldwide. Relationship to electrical engineering. Electronics is a subfield within the wider electrical engineering academic subject. An academic degree with a major in electronics engineering can be acquired from some universities, while other universities use electrical engineering as the subject. The term electrical engineer is still used in the academic world to include electronic engineers. However, some people consider the term electrical engineer should be reserved for those having specialized in power and heavy current or high voltage engineering, while others consider that power is just one subset of electrical engineering, as well as electrical distribution engineering. The term power engineering is used as a descriptor in that industry. Again, in recent years there has been a growth of new separate entry degree courses such as Systems Engineering and Communication Systems Engineering, often followed by academic departments of similar name, which are typically not considered as subfields of electronics engineering but of electrical engineering. History. Electronic engineering as a profession sprang from technological improvements in the telegraph industry in the late 19th century and the radio and the telephone industries in the early 20th century. People were attracted to radio by the technical fascination it inspired, first in receiving and then in transmitting. Many who went into broadcasting in the 1920s were only amateurs in the period before World War I. To a large extent, the modern discipline of electronic engineering was born out of telephone, radio, and television equipment development and the large amount of electronic systems development during World War II of radar, sonar, communication systems, and advanced munitions and weapon systems. In the interwar years, the subject was known as radio engineering and it was only in the late 1950s that the term electronic engineering started to emerge. Electronics. In the field of electronic engineering, engineers design and test circuits that use the electromagnetic properties of electrical components such as resistors, capacitors, inductors, diodes and transistors to achieve a particular functionality. The tuner circuit, which allows the user of a radio to filter out all but a single station, is just one example of such a circuit. In designing an integrated circuit, electronics engineers first construct circuit schematics that specify the electrical components and describe the interconnections between them. When completed, VLSI engineers convert the schematics into actual layouts, which map the layers of various conductor and semiconductor materials needed to construct the circuit. The conversion from schematics to layouts can be done by software, see electronic design automation, but very often requires human fine-tuning to decrease space and power consumption. Once the layout is complete, it can be sent to a fabrication plant for manufacturing. For systems of intermediate complexity, engineers may use VHDL modeling for programmable logic devices and FPGAs. Integrated circuits, FPGAs and other electrical components can then be assembled on printed circuit boards to form more complicated circuits. Today, printed circuit boards are found in most electronic devices including televisions, computers and audio players. Subfields. Electronic engineering has many subfields. This section describes some of the most popular subfields in electronic engineering. Although there are engineers who focus exclusively on one subfield, there are also many who focus on a combination of subfields. Signal processing deals with the analysis and manipulation of signals. Signals can be either analog, in which case the signal varies continuously according to the information, or digital, in which case the signal varies according to a series of discrete values representing the information. For analog signals, signal processing may involve the amplification and filtering of audio signals for audio equipment or the modulation and demodulation of signals for telecommunications. For digital signals, signal processing may involve the compression, error checking and error detection of digital signals. Telecommunications engineering deals with the transmission of information across a channel such as a coaxial cable, optical fiber or free space. Transmissions across free space require information to be encoded in a carrier wave in order to shift the information to a carrier frequency suitable for transmission. This is known as modulation. Popular analog modulation techniques include amplitude modulation and frequency modulation. The choice of modulation affects the cost and performance of a system, and these two factors must be balanced carefully by the engineer. Once the transmission characteristics of a system are determined, telecommunication engineers design the transmitters and receivers needed for such systems. These two are sometimes combined to form a two-way communication device known as a transceiver. A key consideration in the design of transmitters is their power consumption, as this is closely related to their signal strength. If the signal strength of a transmitter is insufficient, the signal's information will be corrupted by noise. Electromagnetics is an in-depth study about the signals that are transmitted in a channel, wired or wireless. This includes basics of electromagnetic waves, transmission lines and waveguides, antennas, its types and applications with radio frequency (RF) and microwaves. Its applications are seen widely in other sub-fields like telecommunication, control and instrumentation engineering. Control engineering has a wide range of applications, from the flight and propulsion systems of commercial airplanes to the cruise control present in many modern cars. It also plays an important role in industrial automation. Control engineers often utilize feedback when designing control systems. For example, in a car with cruise control, the vehicle's speed is continuously monitored and fed back to the system, which adjusts the engine's power output accordingly. Where there is regular feedback, control theory can be used to determine how the system responds to such feedback. Instrumentation engineering deals with the design of devices to measure physical quantities such as pressure, flow and temperature. These devices are known as instrumentation. The design of such instrumentation requires a good understanding of physics that often extends beyond electromagnetic theory. For example, radar guns use the Doppler effect to measure the speed of oncoming vehicles. Similarly, thermocouples use the Peltier-Seebeck effect to measure the temperature difference between 2 points. Often instrumentation is not used by itself, but instead as the sensors of larger electrical systems. For example, a thermocouple might be used to help ensure a furnace's temperature remains constant. For this reason, instrumentation engineering is often viewed as the counterpart of control engineering. Computer engineering deals with the design of computers and computer systems. This may involve the design of new computer hardware, the design of PDAs, or the use of computers to control an industrial plant. Development of embedded systems made for specific tasks, e.g., mobile phones, is also included in this field. This field includes the microcontroller and its applications. Computer engineers may also work on a system's software. However, the design of complex software systems is often the domain of software engineering, which is usually considered a separate discipline. VLSI design engineering. VLSI stands for Very Large Scale Integration. It deals with fabrication of ICs and various electronic components. Education and training. Electronics engineers typically possess an academic degree with a major in electronic engineering. The length of study for such a degree is usually 3 or 4 years, and the completed degree may be designated as a Bachelor of Engineering, Bachelor of Science, Bachelor of Applied Science, or Bachelor of Technology depending upon the university. Many UK universities also offer Master of Engineering degrees at the graduate level. Some electronics engineers also choose to pursue a postgraduate degree such as a Master of Science, Doctor of Philosophy in Engineering, or an engineering doctorate. The master's degree is being introduced in some European and American universities as a first degree, and the differentiation of an engineer with graduate and postgraduate studies is often difficult. In these cases, experience is taken into account. The master's degree may consist of either research, coursework, or a mixture of the two. The Doctor of Philosophy consists of a significant research component and is often viewed as the entry point to academia. In most countries, a bachelor's degree in engineering represents the first step towards certification, and the degree program itself is certified by a professional body. Certification allows engineers to legally sign off on plans for projects affecting public safety. After completing a certified degree program, the engineer must satisfy a range of requirements, including work experience requirements, before being certified. Once certified, the engineer is designated the title of Professional Engineer in the United States, Canada, and South Africa, Chartered Engineer or Incorporated Engineer in the United Kingdom, Ireland, India, and Zimbabwe, Chartered Professional Engineer in Australia and New Zealand, or European Engineer in much of the European Union. A degree in electronics generally includes units covering physics, chemistry, mathematics, project management, and specific topics in electrical engineering. Initially, such topics cover most, if not all, of the subfields of electronic engineering. Students then choose to specialize in one or more subfields towards the end of the degree. Fundamental to the discipline are the sciences of physics and mathematics, as these help to obtain both a qualitative and quantitative description of how such systems will work. Today most engineering work involves the use of computers, and it is commonplace to use computer-aided design and simulation software programs when designing electronic systems. Although most electronic engineers will understand basic circuit theory, the theories employed by engineers generally depend upon the work they do. For example, quantum mechanics and solid-state physics might be relevant to an engineer working on VLSI but are largely irrelevant to engineers working with embedded systems. Apart from electromagnetics and network theory, other items in the syllabus are particular to electronics engineering course. Electrical engineering courses have other specialisms such as machines, power generation and distribution. This list does not include the extensive engineering mathematics curriculum that is a prerequisite to a degree. Electromagnetics. Elements of vector calculus, divergence and curl, Gauss and Stokes theorems, Maxwell's equations, differential and integral forms. Wave equation, Poynting vector. Plane waves, propagation through various media, reflection and refraction, phase and group velocity, skin depth. Transmission lines, characteristic impedance, impedance transformation, Smith chart, impedance matching, pulse excitation. Waveguides, modes in rectangular waveguides, boundary conditions, cutoff frequencies, dispersion relations. Antennas, dipole antennas, antenna arrays, radiation pattern, reciprocity theorem, antenna gain. Network analysis. Network graphs, matrices associated with graphs, incidence, fundamental cut set, and fundamental circuit matrices. Solution methods, nodal and mesh analysis. Network theorems, superposition, Thevenin and Norton's maximum power transfer, Y-delta transformation. Steady-state sinusoidal analysis using phasors. Linear constant coefficient differential equations, time domain analysis of simple RLC circuits, solution of network equations using Laplace transform, frequency domain analysis of RLC circuits. Two-port network parameters, driving point and transfer functions. State equations for networks. Electronic devices and circuits. Electronic devices, energy bands in silicon, intrinsic and extrinsic silicon. Carrier transport in silicon, diffusion current, drift current, mobility, resistivity. Generation and recombination of carriers. PN junction diode, Zener diode, tunnel diode, BJT, JFET, MOS capacitor, MOSFET, LED, PIN and avalanche photo diode, lasers. Device technology, integrated circuit fabrication process, oxidation, diffusion, ion implantation, photolithography, N-tub, P-tub and twin-tub CMOS process, analog circuits, equivalent circuits, large and small signal of diodes, BJT, JFETs, and MOSFETs. Simple diode circuits, clipping, clamping, rectifier. Biasing and bias stability of transistor and FET amplifiers. Amplifiers, single and multi-stage, differential, operational, feedback and power. Analysis of amplifiers, frequency response of amplifiers. Simple op-amp circuits. Filters. Sinusoidal oscillators, criterion for oscillation, single transistor and op-amp configurations. Function generators and wave-shaping circuits, power supplies, digital circuits, Boolean functions NOT, AND, OR, XOR. Logic gates, digital IC families DTL, TTL, ECL, MOS, CMOS. Combinational circuits, arithmetic circuits, code converters, multiplexers and decoders. Sequential circuits, latches and flip-flops, counters and shift registers. Sample and hold circuits, ADCs, DACs. Semiconductor memories. Microprocessor 8086, architecture, programming, memory and I/O interfacing. Topic: signals and systems. Definitions and properties of Laplace transform, continuous time and discrete time Fourier series, continuous time and discrete time Fourier transform, Z-transform. Sampling theorems. Linear time invariant (LTI) systems, definitions and properties, causality, stability, impulse response, convolution, poles and zeros, frequency response, group delay, phase delay. Signal transmission through LTI systems. Random signals and noise, probability, random variables, probability density function, autocorrelation, power spectral density, function analogy between vectors and functions. Control systems. Basic control system components, block diagrammatic description, reduction of block diagrams, Mason's rule. Open loop and closed loop negative unity feedback systems and stability analysis of these systems. Signal flow graphs and their use in determining transfer functions of systems, transient and steady state analysis of LTI control systems and frequency response. Analysis of steady state disturbance rejection and noise sensitivity. Tools and techniques for LTI control system analysis and design, root loci, Routh-Hurwitz stability criterion, Bode and Nyquist plots. Control system compensators, elements of lead and lag compensation, elements of proportional integral derivative controller (PID). Discretization of continuous time systems using zero-order hold and ADCs for digital controller implementation. Limitations of digital controllers, aliasing. State variable representation and solution of state equation of LTI control systems. Linearization of nonlinear dynamical systems with state space realizations in both frequency and time domains. Fundamental concepts of controllability and observability for MIMO-LTI systems. State space realizations, observable and controllable canonical form. Ackermann's formula for state feedback pole placement. Design of full-order and reduced-order estimators. Communications. Analog communication systems, amplitude and angle modulation and demodulation systems, spectral analysis of these operations, superheterodyne noise conditions. Digital communication systems, pulse code modulation (PCM), differential pulse code modulation (DPCM), delta modulation (DM), digital modulation, amplitude, phase and frequency shift keying schemes (ASK, PSK, FSK), matched filter receivers, bandwidth consideration and probability of error calculations for these schemes, GSM, TDMA. Professional practice. Professional bodies of note for electrical engineers include the Institute of Electrical and Electronics Engineers (IEEE) and the Institution of Electrical Engineers (IEE), now renamed the Institution of Engineering and Technology or IET. Members of the Institution of Engineering and Technology (MIET) are recognized professionally in Europe as electrical and computer technology engineers. The IEEE claims to produce 30% of the world's literature in electronic engineering, has over 430,000 members, and holds more than 450 IEEE-sponsored or co-sponsored conferences worldwide each year. SMIEEE is a recognized professional designation in the United States. Project engineering. For most engineers not involved at the cutting edge of system design and development, technical work accounts for only a fraction of the work they do. A lot of time is also spent on tasks such as discussing proposals with clients, preparing budgets and determining project schedules. Many senior engineers manage a team of technicians or other engineers, and for this reason, project management skills are important. Most engineering projects involve some form of documentation, and strong written communication skills are therefore very important. The workplaces of electronics engineers are just as varied as the types of work they do. Electronics engineers may be found in the pristine laboratory environment of a fabrication plant, the offices of a consulting firm, or in a research laboratory. During their working life, electronics engineers may find themselves supervising a wide range of individuals including scientists, electricians, computer programmers and other engineers. Obsolescence of technical skills is a serious concern for electronics engineers. Membership and participation in technical societies, regular reviews of periodicals in the field and a habit of continued learning are therefore essential to maintaining proficiency. And these are mostly used in the field of consumer electronics products. See also: Electrical engineering technology, Glossary of electrical and electronics engineering, Index of electrical engineering articles, Information engineering, List of electrical engineers, Timeline of electrical and electronic engineering.